All right, let's see. Did most people get it pushed over? The usual, about 80% or so submitted in a way that I could download on time. So that seems to be about average with Git submissions. About 20% will get it in later. So if you did not get your Git repo pushed over in a way where I was able to download it, I sent you a note on Canvas. So if you saw that, go ahead and please take care of whatever the issue is and get things pushed over before 8 a.m. on Saturday. Yeah, I think there were probably a number of people who were up late working on it. Because I checked yesterday afternoon and like 9 things had been pushed over, so most of them came in after, somewhere in the last 24 hours. All right, cool. So yeah, I'll get those graded over the weekend, and then Monday we can talk about general comments on that assignment. But hopefully people figured out how to do most of this. Delete again is usually the trickiest part. Um, but hopefully you got most of the functionality working. So any lingering questions before we get started, either on binary search trees or anything we've been doing with sorts? We're going to finish up sorts today. All right, so let's continue talking about heaps, and we'll stick with max heaps. And remember, 2 things about heaps. One, so a heap's a binary tree. It has a shape like a heap, which means it's filled in from top to bottom and from left to right. And for a max heap, each node satisfies the max heap property, which means each node is bigger than its 2 children. And so let me start with a sample heap. So there's a heap containing 3 things, and let's add some data to this. So the way we add, let's add a 15. So we start by putting the number in the next position in the heap. So if the lowest level is filled completely, then we start a new level and we go in at the leftmost spot. If there's space on the lowest level, we simply put it in the leftmost spot there, so that it preserves the heap shape. And then we upheap. And the upheap procedure says compare the number you just inserted to its parent and see if the parent satisfies the max heap property. So compare 10 with its children. It does not satisfy the max heap. It's smaller than 1 child. So swap with the largest child. And it only has 1 child in this case, so that child goes up there and the old root comes down here. And now, starting from here, see if your parent satisfies the max heap property. Well, 15's parent is 20. 20 is bigger than both children. That satisfies the max heap property. We're done. As soon as you insert a node and its parent satisfies max heap, you're done with the insert operation. So that adds a 15. And let's add a 12. So 12 goes in the next spot. And we check its parent is 15. Does 15 satisfy the max heap property? Yes. So we're done. All right, questions about this? All right, so let's add a few more things. Let's put in a 17. Check the parent. 5 is not bigger than both children, so swap with the largest child. 17 goes up here. 5 goes down here. Check 17's parent. 20 is bigger than both children. Satisfies max heap. We're done. Let's add a 50. So put it in the next spot in the heap. That's right here, leftmost position on the bottom row. Check its parent. 17 does not satisfy the max heap property, so swap with the largest child. So 17 goes down here, 50 goes here. Now check 50's parent. 20 does not satisfy the max heap property. It's not bigger than both children, so swap with the largest child. 50 goes up here, 20 comes down here. There is no parent, so we're done. And we have a heap. So each time we do this, we end up with a heap. And in any max heap, the largest thing in the heap is always situated at the root. So that's the addition operation. And the number of things you have to do to add, well, putting it into the bottom spot, that's a fixed amount of time. Upheaping, you might have to upheap all the way up to the root, which means you might have to do this much work. And the number of things from, you know, the thing you just inserted up to the root, that's bounded by the height of the tree. And the height of the tree, especially a tree that's nice and full and fluffy like this, is approximately log of n, where n is the number of things in your structure. So this add operation is order log n. So pretty efficient. Wow, the sun is out. I haven't seen that in like days. All right, so that's insertion. So deletion or removing data is basically the same thing in reverse. So we always remove the largest thing in a max heap. We don't generally search for things. We don't generally remove things that aren't at the root. So max heap, the whole game plan is we want to pull out the largest element first. So the largest element is always at the root. So if we say let's remove, you know, the largest element, we're going to pull out the 50. And once we've taken this out, we need to put something else in its place. What do? We take the last element in the heap. Now it's not the smallest, it's the thing on the lowest level furthest to the right. In this case, that's a 17. So we take 17 and we move that to the root. And now we down heap. So we look at 17, we see if it satisfies max heap. It doesn't. 17's not bigger than its children. So swap with the largest child. And now down heap from here. 17's bigger than its children. We're done. Right? And when you're doing a max heap and you're up heaping or down heaping, you always swap with the largest child. For a min heap, you're going to swap with the smallest child. All right, we're just sticking with max. All right, so let's remove the 20. That's the root. Take that out. Take the last thing in the heap, that's our 5. Move it up to the root. And then down heap. Does not satisfy the heap property, swap with the largest child, which is 17. So 17 goes here, 5 goes here, and we're done. We'll do one more, take out the 17, replace it with the last thing in the tree, which is a 12. And down heap. 12 is not bigger than both children, so swap with the largest child. This becomes a 15. This becomes a 12. Check the heap property there. It's satisfied. We're done. And when we remove, right, removing the root is a fixed amount of time. If we can get to that last node, right, making that the new root is a fixed amount of time. And then down heaping is bounded by the height of the remaining nodes, which is log n. So removing is also order log n. But there is this question of how do we actually find that last node, and we're going to address that in a few minutes. But, you know, right now my last node is here, so I go left, left. If I have something sitting here, my last node I'd get to by going left, right. And it's not clear how to find that last node unless you know ahead of time how many things are in your tree. Because I can't use the values of these to tell me where the last node in my heap's going to be. So we'll have to deal with that, but that's going to be an easy thing to deal with. So insert, remove, these are log n operations.
So there's no guarantee that on any of the same levels that things on the left are going to be bigger or smaller than things on the right, other than just to say that they're going to be smaller than, and the max heap can be smaller than the parent.
Absolutely correct, yeah. So, you know, 12 is bigger than 5, even though it's on the left. Here, 10 is bigger than 5, it's on the left. But, you know, this could have, you know, a 1 and a 4, where the bigger one's on the right. You know, with some stuff here. So yeah, there's nothing we can say about left, right relative values. I'm missing stuff over here for it to be a heap. All right. So how do we build a heap? So you have a set of numbers and you want to turn them into a heap. And there's one fairly straightforward way to do that, which is start with an empty heap and just keep adding in your data in whatever particular order it comes in. And that will leave you with a heap. And the complexity of that, well, each of your add operations is going to be order log n, and if you have n pieces of data, that's going to end up being an n log n operation. But there's a better way to construct a heap, and so this is a really fun algorithm. So let's say we have a set of data. All right, we want to build a heap out of this. So rather than start with an empty tree and, you know, add a 14, add a 2, add a 7, and so on, here's what we're going to do. First, we're just going to ingest this data and we're going to throw it into a tree that looks like a heap. We're just going to worry about that first property, that the thing has to be shaped like a heap. And that's easy to do. To do that, we just take our data in the order that it arrives and we just fill out a heap-shaped thing. All right, so no rhyme or reason. Yeah, that works. No rhyme or reason to what's where, right? It's just whatever order the data happen to come in. All right, so it's shaped like a heap. And now we do something called heapifying. And the idea of heapifying is the following. We start with the last thing on the bottom row, so the rightmost entry on the lowest row, which is our 111. And we down heap. So we say, does 111 violate the heap property? Well, it has no children, so there's nothing to do there. Yeah, that's a real term. Isn't that awesome? So 111 is fine. And 999, it has no children, so that satisfies the heap property, and so on. And so all of these, we're not going to have to do anything for. So now we come to the 19 and we say, does this satisfy the max heap property? And it doesn't. So we're going to swap this with the largest child. So this becomes 999, and this becomes 19. And then 19 has no children, so we're done. Yeah, like spaghettification. Is that a real word? Should be a programming term. All right, now we go to 100. 100 satisfies the max heap property, so that's fine. 6 does not satisfy, so we swap with the largest child. So we put a 50 here and a 6 down here. And 3 does not satisfy the max heap property, so swap with the largest child, which is 85. And 3. And now we go up to the next level. 7 does not satisfy the max heap, so swap with the largest child, which is 999. And this becomes 7. And 7 does not satisfy max heap, so swap with the largest child, which is 111. All right, go on to the next node, 2. Swap with the largest child, 85. And 2, swap with the largest child, which is 43. And now we got one more node to do, which is 14. Swap with the largest child. So there's 999 and 14. Does not satisfy max heap. Swap with the largest child, which is 111. And this becomes the 14. Swap with the largest child, which is 19. And this becomes our 14. And we've done the first node and we're done. And we've got a heap. Yeah, a little bit like bubble sort. Alright, so it's still shaped like a heap, right? Which is guaranteed. And each node is bigger than its children, as long as I didn't mess up somewhere. I think we're good. Right, so that's a max heap. And it turns out this has a really fantastic order of complexity. So we started with 15 pieces of data. And regardless of what the actual values are in here, right, the values depend on the order of the data that you use to build your heap-shaped thing. But regardless of the values, if we've got 15 pieces of data, the 8 things on this lowest level, the 8 leaf nodes, we don't have to do any work. They have no children, so by default they satisfy the heap property. Alright, then we moved up one level. And for each of these nodes, at most we have to do one operation. We're going to have to down heap once, swap with the largest child, and then we'll be at another leaf node. And there's 4 of those nodes. So think about this, 15 pieces of data, half of them, no work to do at all. A quarter of the remaining ones, one operation. So 3/4, 75% of your tree, you have to do either no operations or one operation. And in fact, the majority of those, you don't have to do anything. If we go up one more level, you might have to do 2 operations. You might have to down heap twice. So this is half of your data, this is a quarter of your data, this is an eighth of your data. The total of that is 7/8 of your data, right? 87.5% of all your data, you have to do either no work, one operation, or two operations. So this is actually better than n log n, right? This will actually turn out to be order n, which is really cool. And the calculation of this is a fun exercise. You get into you know, infinite series and convergence of infinite series. So it might be 2n, but that turns out to be the same as n. There's some constants in here, and there's some additive constants. And you can find lots of discussion and analysis of this complexity, including average case and worst case. But it turns out to be linear instead of n log n, and that's really cool. All right, so what are heaps good for? Well, we've talked about stacks and queues, right? And a stack has this property that the last thing you put into your structure is the first thing that comes out. A queue has this property that the first thing you put in is the first thing that comes out. What about a max heap? Could we paraphrase a max heap in some structure similar to this? Some phrasing similar to that?
The biggest thing is always going to come out first?
Yeah, the biggest in is the first out. So this is like a BIFO. And a min heap, that's a SIFO. These aren't official terms. I just like saying them. It's Silly Word Friday. So max heap, the largest thing that you've put into your collection of data, is the first thing that will be removed. And then a min heap. Min heaps are just like max heaps, except, you know, do everything backwards. So smallest in is the first thing that comes out. So a min heap, the smallest thing is always sitting at the root. When you want to add, you still add to that last position and you upheap. When you want to remove, you replace the root with the last thing in the heap and you downheap. But the heap property is the opposite. You have to be smaller than both your children to satisfy the min heap property. So these are different kinds of structures. And they pop up. The most common example you'll find for an application is a priority queue. So a priority queue is like a plain old queue, but it allows you to have not just, you know, entries in your queue in a first in, first out, but you can have priorities assigned to them. So you've got job scheduling going on in an operating system. Single CPU, single core, so it can do one thing at a time. And imagine, you know, you've got some job 1, which is being executed, and you've got jobs 2 and jobs 3 waiting to be executed. So job 1 runs for a few milliseconds, and then the operating system takes everything from job 1, stores it somewhere, register values, program counter, all of that stuff, and it pulls in the context for job 2 and executes that for a little while. And then when that time slices up, it goes on to job 3, and when that comes up, it goes on to job 1, and so on. And maybe while job 1 is executing, job 4 appears. So job 2 will get a time slice, and job 3, and after job 3, now job 4 runs. Okay, this is the queue type behavior of job scheduling. We don't want to execute job 4 as soon as it appears. We're going to let jobs 2 and 3 get their time slice that they had coming, and then execute job 4, and then go back to job 1, and job 2, and maybe job 2 finishes at this point, and job 5 comes in. So then 3 and 4 and 5 and 1 and so on. Well, while this is happening, there's system level events that take place, and these might be higher priority jobs. So maybe while job 3 is executing, system job 1 comes in, followed by system job 2. So when job 3 finishes, instead of going on to the next thing in this queue, the system would say, hey, there's something in this higher priority queue, and it would go ahead and it would start executing system job 1. And it would do that for a little while and then go on to system job 2, and maybe that finishes and it goes back to system 1, and then when that finishes it looks for the highest priority job ready to go, and that would be job 4, and so it goes ahead and it runs job 4. So how do you store the priorities of these jobs in a way that lets you know which job has the highest priority? Max heap would work really well. So you'll see these things called priority queues, and it's basically, you know, a set of queues where each queue has a different priority, and in addition to taking, you know, the first thing out, taking out the first thing that was put in, you also take from the queue with the highest priority first. So you can use a max heap for that. And you know, if you look at your job schedule, there's priorities associated with each job, and the smaller the priority, the higher the priority of the job, right? So negatives are very high priority. So 20 is kind of the default user priority, right? So my browser and my screen recorder and stuff like that are running at priority 20. My audio system is a higher priority. That's got a priority of 9. My video driver, my NVIDIA card and so on, that's super high priority. That's why my CPU keeps overheating, right? And these system jobs, these things owned by root, like these, right? Those are priority 0. So they're higher priority than user, but lower priority than some other stuff. And so you know, every operating system usually has a notion of different priority jobs, different importance level of jobs, right? And the idea is, you know, if my browser has to wait a few time slices to continue its work, that's not a big deal, right? A browser is usually being viewed by a human, or it's doing some download and it's bound by network transmission time or human interaction time. Whereas, you know, the graphics display is pretty critical, because if that's not doing everything it needs to do, my display is going to lag, my windows are going to tear when I move them and things like that. So typically we have these different priorities of jobs, and you often see a max heap being used to implement those pieces of the operating system. Have you looked at the source code to see if it's a max heap? What might that look like dealing with memory, etc.? I have not dug into the source code for an OS in quite a few decades. Last time I did that was when I was an undergrad, and we were taking apart the school's mainframe at night. But you can download source code for you know, Unix. That's all open access. But it's probably a bit of an adventure trying to dig into that. But you could try doing some grepping for like heap or something like that. And this is one of these things where, you know, a decent OS textbook, or a course in OS, will get you, you know, the theory, something, you know, more detailed than this, but kind of along those lines. But it's a totally different experience to actually dig into code And if you're going to do this, I would suggest, try something smaller than Unix. Um, dig into CPM or something like that. Um, and and see if you can find this stuff. CPM didn't do job scheduling, I don't think. But dig into some kind of modest operating system, or better yet, try writing your own. Right. This is a great exercise if you want some practice coding and you want to work with some of these concepts. Write yourself an operating system. Right. Run it on an Arduino or a Raspberry Pi or something, and do a few basic things. Manage a few files, execute a few programs, um, and see what kinds of issues you run into. Um, and yeah, this definitely changes between operating systems. You were doing what? Yeah, when I was an undergrad, we got permission to take apart the school's computer on Saturday evenings, so we could start at 10 p.m. We had to finish by 6 in the morning. So we'd fuel up on pizza and other junk food and Chinese food, and we just shut out all the users and then just take this thing down and do various things to it, including rewriting its instruction set because it was microcoded, and so we change the microcode and create new machine language instructions and stuff. Changing priority and crash systems have done wrong though, right? So you can on Unix systems, you can set the priority of jobs using the nice command. So nice lets you run a program with different priority. If you're not a privileged user, you can only decrease your priority, you can't increase it. But if you're root, you can bump up the priority of jobs, and you can definitely hobble your system that way. So if you make, just a simple infinite loop and you run that with high priority, you can make it very difficult to even get enough CPU time to interrupt that job. But it's not a bad thing to play around with on your own system, and see how that works. And this is probably a good way to dig into the priority scheduling on Unix if you want to go that route. Now, nice is just going to set up probably just an integer somewhere which says what the job's priority is, but if you were to watch that location in memory and see what touches it, you'll probably be able to find the code that's actually looking at that value. And this is where it's fun, running Linux on your own machine, especially if you take the cover off and you, if you have an oscilloscope, or better, a logic analyzer, or better yet, an emulator like VirtualBox, right? You can start doing all kinds of experiments. All right, but I'm geeking out now. So let's talk about implementation of heaps. So the downside to heaps is, there's some trickery that has to go on with finding the last entry in the heap, which could be, in the left subtree of the root or the right subtree of the root, and so on. Let's see, a lot of testing for tic-tac-toe is done in DOSBox. Yeah, so if you have a way to play around with an environment that you can actually get into, sort of hand of God mode, you can have a lot of fun and learn a lot of stuff to in developing stuff. So heaps, we need to be able to, figure out where the last thing in the heap is. If your heap looks like this is the last one, right? Left, right. If your heap looks like this, your last node is to the right and to the right. And if you know how many nodes are in your heap, you can actually figure out how to get to the last one by looking at the binary representation of the number of nodes. And I believe that will tell you whether you want to go left or right at each level. The other issue is when we're upheaping, we need to look at our parent. And remember, binary trees, generally we have pointers to the children, but the children don't have pointers to the parent. And so we need some way to move from a node up to its parent node so that we can check to see if the parent satisfies the heap property. And it turns out we can cut out a lot of those complexities by changing our implementation of a heap. Instead of using nodes which have data and a pair of pointers and look like a binary tree, we can implement a heap with just a plain old array. And this is like ridiculously fun. So let me make an array over here. It's weird that it came out of power of 2. And let me make a generic looking heap over here. And here's how we're going to store this heap in the array. We're going to skip element 0. And we're just going to start going through our heap from top to bottom, left to right. And we're going to store each element in the next location in our array. So this is going to be A, B, C, D, and so on. And these aren't the values. I'm just using the letters to represent these nodes. But, you know, obviously this is not a heap because E is not bigger than J. These are just names for the nodes, right? And when you have an array of data, you always need to know what the size of that is. So I'm going to have a variable called heap size. And I'm going to set that to the number of things in my heap. So I got 10 nodes in here, so heap size is 10. And we've solved our first problem pretty quickly now. If I want to know the last thing in the heap, it's just the element stored at heap size. And if I want to remove the largest entry, right? Well, the largest entry is the root, and the root is always at location 1. So find the largest thing in the heap. It's just, you know, I'll call this heap. It's just heap bracket 1. That's never going to change. And, you know, first I check to see heap size. If heap size is 0, the heap's empty. Otherwise, the largest element is heap bracket 1. If I want to replace that with the last element, what do? Heap bracket 1 equals heap bracket heap size. Right? So heap bracket heap size, that tells me the last element in my heap. And if I want to move that to the root, that's just something like heap bracket 1 equals heap bracket heap size. And after I do that, let's decrement heap size. So that one statement does this business of finding the last thing in the heap and moving it up to the root. So that's pretty simple. And if we're going to add something, say we want to add a k to our heap, well, what do? We increment heap size and we store at that index. So this is just something like heap bracket plus plus heap size equals whatever your new data is. So if I want to store a k, I'll increment heap size to 11. I'll store my k right here. And now that's what my heap looks like. So adding and removing, straightforward operations. The other business is down heaping and up heaping. So let's make a table. Let's make a node index. Let's look at the left child and its index. And let's look at its right child. And that right child's index. So let's look at node A. So the index of A is 1. Its left child is B. Its right child is C. The index of B is 2. The index of C is 3. Let's pick a different node. Let's pick node C. So what's the index of C? Three. And what's the identity of C's left and right child? What's the name of the node on the left and the right? Those are F and G. All right, and what is the index of F and G? Awesome, let's do one more. So let's look at node E. I don't know what these little bugs are. I suspect my bananas, but the bananas are still not ripe. I got these little flying bugs. They don't seem to do anything. All right, so node E, what's the index of E? Everybody can play along here. SpongeBob dollars. There we go. E is an index of 5. Who are the left and right children of E? J and K, and what are their indices? 9 and 10. J and K, 10 and 11. Right, so we're just reading off data, right? Here's E, left child is J, that index is 10. Right child is K, that index is 11. All right, so let's hypothesize. So what's the formula for the left child of N? Node N. Or more precisely, what's the formula for the index of the node on the left of the node whose index is N? To N. And what about the right child? You got it. So we can move from a node to its children by just doubling the node number, or doubling the node number and adding 1. If I want to find the right child of D, D is node 4, the right child is 9. 9 is I, that's the right child of D. So as we're down heaping, if we want to compare a node's value to the value of its children, we just compare heap bracket N with heap bracket 2N and heap bracket 2N plus 1. And if we want to swap, right, we just swap heap N with whichever of those two other elements is largest. And so that's straightforward. And to go up, if we want to find the parent of node N, well, the parent of 10 is 5, the parent of 11 is also 5. The parent of 6 and 7 are 3, the parent of 2 and 3 are 1, so hypothesize a formula for finding the parent of node N. Yeah, perfect. So take n divided by 2, and if it's not a whole number, make it a whole number. So if I'm starting with k, that's an 11. If I want to find its parent, that's 5. That's our e. If I want to find 5's parent, it's 2. That's our b. If I want to find 2's parent, that's 1. That's our a. If I try to find a's parent, 1/2 will turn out to be 0, and 0 is not a valid index in our heap. That's the other way I know that a is the root, but the root's always at location 1. So casting to an int will truncate it, which for positive numbers will basically round it down. And these are always positive indices, so truncating is fine. You can also shift right, and that throws away the rounding error and divides by 2. All right, so these are trivial operations, right? Building the heap, we just keep inserting into, element heap size being incremented. Finding the root is just this thing. Finding the last element is just the element at heap size. And we can move down the tree by just multiplying by 2, and we can move up the tree by dividing by 2. So this is really easy to code, right? And we always fill in, our array starting from element 1. And if we've got 11 elements in the array, they'll be the first 11 elements. And if we want to add more stuff, it's always going to go at the end. So we never move things around in here. To simply add something to the bottom of the heap. And so if we had to get a larger array, we could, copy this array somewhere else that has more space. And so this works really well. Speaking of bitwise, at some point where you talk about bitwise operations, let's see. I don't think I actually talk about that. We should. So I think we touch on that in 121, but I don't think it comes up in 224. If we have time, that would be a good thing to talk about. But that C book that I posted, that I wrote, that has a chapter on bit operations, and I put that in specifically to kind of cover whatever might be missing from past courses. Yeah, that would be a good thing to talk about. I should rework my syllabi actually in the future, or just do that in 224. Yeah, if we have time, we can go through that. All right, so that's heap, that's sorts. That's pretty much everything I wanted to do. I'll probably try to put together some practice problems over the next few days and post those to let people work on some of the stuff with sorting and heaps and so on. So what's our game plan here? I will post PA5 over the weekend. We'll talk about it on Monday. It'll be due a week from Monday, so you'll have a week, including a weekend, to work on that. And that's going to be something involving dynamic programming, which we'll start talking about on Monday. All right. So that's all I got. I will see you in 2:15 if you're there. Otherwise, have a fantastic weekend, and I will see you on Monday. Oh, yeah, and SLPs are due on Monday. Don't forget those.